Hello everyone! What I'm making here is a little bit of a recap video, just pointing out some things from the discussion forum for this week. Obviously, this is going to be a finite length video, so I'm definitely not going to be highlighting every single post, but I'll pick out a few that pertained in important ways to things that are relating to our class content. So the first one I picked out was a post that asks how many are in the bag. And what we have here is a representation for an algebra equation. So how many, it looks like these are some kind of small candies, and clearly that's a question that could be useful if we're planning on having some candy. So B, according to what we seem to have here, is the number of candies in a bag. So it's implied here that every bag has the same amount of candy in it. And what we have here is, on a balance beam, something that gives us a meaning for the equation 9 plus 2b equals b plus b plus b plus 4. So let's see how we can work with this to find out how many we have in each. Well, one thing is we could rewrite this b plus b plus b as 3b. So we could, without changing really anything to do with the value, we could write it as 9 plus 2b equals 3b plus 4. Now another thing we could do, and I'm going to actually diagram this out. So we have 9 individual candies here. I'm going to represent those with dots, and 2 bags that hold each an indeterminate amount of candy. And on the other side, we have 3 bags, again, each holding the same but indeterminate amount of candy, and 4 individual candies connected to each other by a balance beam. Okay, one thing we can do is, it would be convenient if we only had an unknown on one side. So I'm going to take a bag off of each side, and then another one. So what I have now, and I'll make room for a fresh copy of it, is that 9 candies balances with 1 bag and 4 candies. We can also do that in algebraic notation by subtracting 2b on each side. And then what we have here is that 9 is the amount of candy in 1 bag and 4 more candies. But what we really want to know about is 1 bag. So we can take off 4 candies from each side. Like so. And again, we can do that symbolically, subtracting 4 on each side like so. And so we expect that 5, just like right here, would be the amount of candy in 1 bag. Okay, so is that true? Well, we should definitely check. I'm going to put a box around this for a minute because we think it's our final answer, but let's go ahead and check. So 9 individual candies plus 2 bags of 5 candies each. Well, that would be 2 times 5 is 10. So 19 candies on our left-hand side. Okay, but on the other hand, what if we had 3 bags of 5 candies each and only 4 individual candies out there? Well, that would be 15 plus 4, so 19 on each side, so it really was equal all along. So 5 really is the number that works, And so I'll give us a star because I believe that we did this correctly. I mean, the number works. You can't argue with what works. So speaking of simplifying according to the order of operations, which is a step we use very often, this expression to simplify also got posted as a puzzling problem. And this is an interesting and important one because the disagreements that people have about this expression really get to the heart of this symbol right here and the implied multiplication that happens right here. Now, what the book says about the order of operations is that multiplication and division count as a single step, and within those you strictly work from left to right. So that would tell us that what we have here is 3 times 1 plus 2. And then within the parentheses we'd say, okay, well, 1 plus 2 is 3. So the official right answer to this expression would be 9. But the way you read the problem can matter, and if you happen to know that the person meant this other thing, it's, it's polite to them to read the problem how they meant it. What some people will do is they'll write this when what they really mean is 6 over 2 times 1 plus 2, which is a completely different expression. And so what it really gets at is, in this second version, they're taking the implied multiplication as a slightly higher priority than the division. So this is not mathematically the same as the previous expression. But it's such a common thing to do that there are actually calculators out there that will read it this way because they know that that's what people mean. And when you follow this through, it's like, okay, well, we'll do what's in our parentheses first. So copying over, that will give us 6 over 2 times 3, which is just 6 sixths, which is 1. You can tell by sketching out 6 sixths. Clearly that's a whole, and it's also 6 of them. So this is the actual right answer, but this is a common mistake, and the way we avoid having that common mistake come up is if we actually mean this, write it out this way or put some parentheses around your denominator, but preferably for algebra class, and here's the real takeaway from this message. For an algebra class, avoid the division symbol by writing it as a fraction instead. And I know fractions, right? But there's no mistaking with a fraction what the two things you're dividing by are. They're whatever is in the top and whatever is in the bottom. So for communication purposes, fractions actually are better in this context. Again, I know it seems weird, but this time it's true. So part of the reason I brought that up is some people's method on this problem that actually I was the one who posted in our discussion group, some people's method was to just punch it straight into a calculator. And calculators are awesome. You should definitely offload a lot of your arithmetic to the calculator to save your brain some capacity. Okay, my lizard's all right. My silly little lizard here just jumped really hard against the cage wall and smacked his nose against it, but he's moving, he's good. Okay, so calculators are great, but you should never trust a calculator with a problem that you couldn't have done on your own, because you don't know if the calculator will do it correctly. So instead of overly trusting a calculator with this, I'm going to do a little creative rewriting. So One thing I know about 2 to the power 300 is that that's the same as 2 to the power 3 times 100. I could similarly write 3 to the power 200 as 3 to the power 2 times 100. Well, what does that give me? Well, from one of our sections this week, the topic was exponent properties. And one thing that you would have noticed then is that if you have, say, a to the power b, then to the power c, you can rewrite that as a to the power b times c. You're allowed to reverse that also. So if you have a to the power b times c, and it would be convenient to do so, you are allowed to write that as a to the power b times, or to the power c. So I am going to rewrite this as 2 to the power 3 to the power 100. And I'm going to write this one over here as 3 to the power 2 to the power 100. Well, I know 2 to the power 3, that's 8. So what I have here is 8 to the power 100. Well, 3 to the power 2 is 9. 3 times 3. So what I have here is 9 to the power 100. Okay, so I know that 8 is less than 9. Simply by counting. And I expect that if I multiply 8 by itself several times, that will still be less than multiplying 9 by itself the same amount of times. For example, 8 squared is 64, 9 squared is 81. 8 cubed would be a good calculator problem. So let's see. 8 to the power 3 would be 512. 9 to the power 3, I want to say that's going to be 700 and something. Yes, 729. So when you multiply 8 by itself or 9 by itself the same whole number amount of times, the one with the base of 8 comes out less than the one with the base of 9. And that tells me that this right here is bigger than this other one right there. That 9 to the power 100 is bigger than 8 to the power 100. But since that's just these same numbers right here, I didn't do any value changing things through here. I just did clever rewrites. That tells me that 3 to the power 200 is bigger than 2 to the power 300 because it has a larger base when you convert it to the same power. Okay, so that's what I have for you for the recap from the discussions this week. For this coming week, make sure that you are posting more problems that are pertaining to things from this class. Now, I know some of you really have fun with the just random arithmetic puzzles, and it's great to post some of those, but make sure you're posting some algebraic problems instead. And remember, it can be a problem out of your homework for your 13-14 class, so you kind of get to double dip on that. Okay, so I will talk to you all later.